expression. So it's basically a sinc function. It's sine cutoff frequency omega c divided by 5n divided by that. Basically a sinc function for n non-zero, and for n equals to 0, you can simply show that the result at b at time 0, it should be omega c divided by 5. So this is our desired impulse response back in the time domain. And very soon we realize that what's the problem? You remember the problem? The problem is that it's just infinitely wide in both directions, right? So such kind of impulse response cannot even be stored. So don't all right? So there's no way we can implement this system. Okay, now, so the issue is that now the impulse response has some sinc envelope with zero crossing somewhere. Yeah. So last time I remember Stephen Ha. Stephen, are you around? Yeah. Stephen, are you around? Last time we had a fellow student by the name Stephen who suggested I still remember last time we discussed the example of color frequency. What is the color frequency? Pi over 4, for example, right? 1/4 of the Nyquist frequency. Pi corresponds to Nyquist frequency. Okay? So you have want to design a low-pass filter, and very soon realize that, yeah, sure, the zero crossing is every 4 samples. We reach the zero crossing every 4 samples, and that's our infinitely extending impulse response, which cannot be implemented. Because there's simply no way that we can store this impulse response. So what should I do? What should we do? We suggest that let's just keep the range. Okay, so our recommendation is, how about we decide a large enough n, so we'll just keep the range from -n to +n. Just keep the range. Keep this range, okay, from -n to +n. And of course, this is fine domain. Okay, this is fine domain. Now, so just keep this part and omit and just throw away anything outside this range. Throw them away. So our recommendation goes this way. And this is actually our first design. So let's say that we design, this is a design, we call it a design. So let's say the result of our design is called an impulse response with a subscript n, denoting how long we are going to, what's the range we are going to keep the impulse response. So Hn is basically equal to a window function. Remember window function. The window function times our desired response, where W is simply 1 if in this range, and 0 elsewhere, meaning that we are going to throw away basically everything outside this range. So far so good, so that's where we were at last time. Okay? Throw away everything, go home. No, we don't need it anymore. See you next time. See you next semester. Go home. Drop it. We drop everything else. And there's one little tiny issue we need to classify. Okay? We're not clarify, so not classify. Clarify. We need to clarify one thing, and that is about what we call causality. Right? So if under this definition, we had a remark saying that, well, now H of n is not all 0 before time 0. Before time 0. It's true. So strictly speaking, this filter is not causal. This impulse response describes a non-causal LTI system. So let me just tell you that in the end, in practice, you just don't worry about it. Store everything. Store everything. Store this long sequence of numbers, 2n plus 1 samples, right? 2n plus 1 n on each side plus the middle sample, 2n plus 1 sample. Just store them, everything of this, into an array. Okay? So technically, if you just store them into a long array with long array with 2n plus 1 elements, 2n plus 1 samples, store them in an array and call it, so your final design really is your age, shifted to the right by big N samples. That makes sense? Otherwise, this time index starts at minus n, so we need to shift everything to the right by big N samples. Okay? So that is to say your final design, will be this h of n, but shifted to the right by big N samples. That's your final design to make everything. Now this becomes causal. It becomes causal and you store everything, all the samples in an array, and you're ready to use it in convolution. The way we apply a filter is to convolve this impulse response with any given input. Okay, is that clear? So this is the way for implementation. So far so good? But that being said, later you'll find that you'll realize that it's easier to discuss this. It's easier to keep using this non-causal version. And the reasons will be clear today. Okay? So it's easier to discuss, so keep our discussion in this. So assume that this is our design. It's easier for discussion purposes. And the main reason is because, note that this design has a nice even symmetry. Note that it has a nice even symmetry. Therefore, we know that if we take the Fourier transform, is real everywhere. And that's the main reason why we prefer to continue our discussion using this. Just think of this as your design, as our design. It's easier for discussion, rather easier than that. Shifting to the right introduces another linear phase shift. So not a big problem, but it's really, you'll see, that this makes our discussion easier. Okay? This makes our discussion easier. Okay, so I think we covered this time. These are all the recap from last week. But last week also, in the end, I think we also mentioned that when we multiply two, so here this expression has a nice, a nice way to look at it is that now our design is to multiply the ideal response with the window function in the time domain. Right? And we know that there is a convolution theorem of the second kind, if you will. If you will. There's a convolution theorem of the second kind which tells us that when we multiply two signals in the time domain, what happens in the frequency domain? Multiplication in one domain, convolution in the other domain. Okay, so that's about, so here it's also true. Because of this, next, because of this multiplication in the time domain, we know that when we take the Fourier transform, our desired response. Actually, this is a sloppy notation. I should write H N E J omega. But you know what I mean. The resulting spectrum after multiplication in time domain, the resulting spectrum is going to be the convolution of two spectrums in the frequency domain. Okay? Now we call this the notation. The way we write it is that now we have big omega convolved with big G in the frequency domain circularly. Circular convolution. What does that mean? That means by definition is 1 over 2 pi, and to refer to my note, convolution in the frequency domain has a very nice expression. A very nice expression of G. Doesn't matter, so it's still the idea is still the same. Flip one of them now. So now theta becomes our domain variable. Omega is omega right here. Okay? So how do we do here? Here we put in G theta. So that's a convolution. This tells us what's going on when we convolve two spectrums in the frequency domain. And of course, the range of integral is from minus pi to pi. So next, we are going to look at the frequency response. Now we know that after truncation, that's enough, truncation. This is an action of truncation, to truncate. Truncation. If you just set everything else to 0, that's to truncate, okay, to keep this middle part. After truncation in the time domain, we expect that our response what should happen back in the frequency domain. Mathematically, what should happen is in the convolution, our ideal response, remember this is the ideal response, and what is big W? Big W is the Fourier transform of our window function. Okay? If you take the Fourier transform, it goes to big W of omega. That's the Fourier transform, the spectrum of our window function. Okay? So technically we need to, there are two tasks. So let's say work item number 1. How about we calculate explicitly big W of omega? I think that's a good exercise. We'll do it. Okay? Let's calculate big W of omega, the spectrum, the Fourier transform of our window function. We can calculate it. And secondly, let's visualize what's going on. Okay? How about we visualize the convolution of G and W? G being our ideal response. So that's what we're going to do next. How about we visualize? We can visualize the convolution. Let's try to visualize what happens when we convolve the Fourier transform of the window with the ideal response, ideal low-pass response. Okay? So I think that we can spend a few moments to work out these two items. So far so good? Now, shall we proceed to work out which? I think we can work out the first one first. Okay? So first one first. But I probably need this much space, I understand. Okay, so how about calculate? Let's calculate big W of omega, the Fourier transform of the window. Okay, we'll do it right here, and then we will discuss the effect of convolution in the frequency domain. Okay? So later we'll discuss the effect of convolving G with the Fourier transform of the window. Okay? So that's later. So coming to this part, big W of omega. Big W of omega. Big W of omega. So let me actually be more careful using the more accurate notation, not the sloppy one. So the Fourier transform of the window, by definition, we have seen this that a lot, should be summation over O(n), right? Just seriously, summation over O(n) W e minus j omega n, right? Good old definition of DTFT. Yeah? But then, W has a range. So this n can just start from minus n to big N, because that's the range where W is not zero, right? And when it's not zero, W is all one, right? W is all one. W is all one. It is finite in a range. So wow, it's pretty simple. It's actually a very simple expression. It's actually a very simple expression. It's just I think we do have room. Just seriously, it's just E J big omega n, E J small omega, sorry, big N minus 1, and so on and so forth. And then when small n is 0, we have 1, and then continuing this summation, E minus J omega, and all the n to E J omega n with a minus sign. Okay? Seriously, this is the first transform of our wisdom. No secret. There's no secret here. Just sum everything according to the definition. Right? Then what's next? What's next? What's next? This is actually a geometric series of finitely many terms. 它这个等比级数it's a geometric series of how many terms? Of 2n plus 1 terms. Okay? Where the first term is E J omega big N, and we just apply the formula of geometric series, right? 1 minus that ratio, the ratio is E minus J omega, and that ratio, and on top we have 1 minus E minus J omega. How many terms do we have? We have 2n plus 1 terms, right? We have 2n plus 1 terms, so just put in 2n plus 1 right here. Yeah. And from here, there are some tricks that you can apply. Okay, so it's easier. Let's just for now keep this term right here. Yeah. And then what's here? So let's try to because the final expression is sine something over sine something. That's a hint. I remember the answer. Okay? I just did it half an hour ago. So, but this might come a bit faster. Everything here is pretty straightforward. So let's just proceed. Just continue. Continue from here. I suggest that let's extract E. Maybe at bottom we work on this part first. Okay, it's easier. So let's extract E minus J half of the angle. Extract that. Right? Extract that, and then now we have E plus J half of the angle minus E minus J half of the angle, and that gives us the sine expression. Now the sine comes out. Okay? That's an NG sine. The sine function will come out with the. So on top we similarly, right? On top we can work it out similarly. Now work it out similarly. What's the term we extract? We extract E to the minus J half of that angle. 一半, half of that angle. Okay? Half of that angle is omega. Be careful, 2n plus 1 divided by 2. Yeah. Extract that so that inside the parentheses we have a nice symmetric expression of E plus J omega half of that sample minus E minus same thing. Same thing. Same thing, okay? Same. I'm running out of my space, but you know what I mean. You know what I mean. So finally, we can organize our expression for a final kind of bookkeeping. So here we have, let me use another color. Use another color. So we'll, of course, put everything here together, okay? Everything here should be put together and miraculously, 奇迹似的, what's happening? that, and that. Right? Miraculously, hopefully I didn't make a mistake. Miraculously, well, miraculously, this is 1, right? 奇迹似的, amazingly, wonderfully. This is 1, and so as I promised, so what's on top? Now we have the ratio on top, we have 2j times sine that angle. Omega 2n plus 1 divided by 2, divided by 2j at the bottom. This part is simply 2j sine omega divided by 2 and 2j cancel out. This is our final expression. Okay? So our final expression taking the Fourier transform of our window function. Not hard. Okay? Just be careful along the way. In each step, you can derive, you can convince yourself that indeed the Fourier transform of the window, of this window, called rectangular window actually. This window is all 1 in the ray, 0 elsewhere. If you take the Fourier transform, there's a closed form expression actually in this notation. So finally, let's also try to draw a sketch. Now, I like sketching. Let's draw a sketch of big W of omega. Okay, shall we do that? Let's draw a sketch. So it seems that here, first of all, when omega is 0, note, 这边是我的笔记序号。Note, when omega, yeah, let me just put it, the big W of 0, the spectrum, the DC value of the spectrum is, you can either use the L'Hopital rule or something else. We just use the L'Hopital rule, omega here, so the ratio should be 2n plus 1, one way or the other. Okay, so omega 0 is 2n plus 1. Actually, I want to draw an even bigger picture right here. Let me draw an even bigger picture right here. n plus 1 for big omega at 0 frequency. 2n plus 1. And then also because of the sine, 2n plus 1 divided by 2 times omega, so this spectrum has 0 crossings in the frequency domain along the frequency axis. Okay? So where are the 0 crossings? That remains to be figured out. Okay? So can you tell me where are the 0 crossings? Where, at which frequencies do we have 0? So I explained initially 0 crossing. The first one should occur at which frequency? The first one should occur at, I hate this. The first one here, which frequency? This frequency should be such that omega 2n plus 1 divided by 2 equals to pi, right? So therefore, that frequency equals to, this frequency equals to 2n plus 1. Seems that that's the answer. The first 0 crossing occurs right here. Yeah? The first 0 crossing occurs right there. Okay? So the first 0 crossing occurs at 2 pi divided by 2n plus 1. That's the first 0 crossing. And then the 0 crossing appears like in equal spacing. Equal spacing, so we should expect something like that, 0 cross. And then at 2 times that frequency, another 0 crossing, 3 times, yet another 0 crossing, while the magnitude gradually decreases because sine 2 omega divided by 2 increases. So we have the Fourier transform should look like, let me just go back to my white chart, should come up and come down and gradually getting smaller. So that's our Fourier transform of the window. So it actually has a closed form expression. Yeah, not clear? This is the Fourier transform, the DTFT of the window function. Okay? So for some reasons, I would suggest that because this looks like a sinc function which could be potentially confusing. Because on one hand, we have a sinc function in time domain because we are designing a low-pass filter. But on the other hand, when we multiply the ideal response in the time domain with a window function which is rectangular, just unfortunately, the resulting spectrum is also looks like a sinc function. It's not exactly sinc because this is sine divided by sine. There we have sine divided by not sine. Not exactly the same, but they do look similar. Okay? So may I suggest, and this is just a suggestion, you don't absolutely have to follow my suggestion. I suggest that let's change our perspective. 换个角度想啊。Because now we just vaguely refer to this as the main lobe. The central part, this part, this part with a big surging positive amplitude, should I say, we'll refer to this part as the main lobe in the frequency domain. Main lobe. In Chinese, sometimes it's translated as main lobe. Okay, main lobe. Whereas all the other things, other lobes right here, this one here, these are referred to as side lobes. Side lobes. Side lobe. Plural. Okay? In Chinese, side lobe. Side lobe is plural, 复数. One side lobe, two side lobes, three side lobes, four side lobes, and you know that, plural. So that's a bit of our terminology, our jargons. Just vaguely, just forget about that. Actually, we have a close expression. That's nice, but that's not super important. Okay, it's nice, but it's not absolutely important. So let's just vaguely see the result as it has a main lobe in the middle and the many side lobes on both sides. Okay, done. So that concludes our first work item. Now we have calculated big W. Okay. So next, we are finally ready to visualize what will happen when we convolve our ideal frequency response with the Fourier transform of the window. Okay, now let's visualize. According to this formula. Okay. So according to this formula, we are going to put G, fix G, but shift big W. Okay, we're going to shift big W to the right by. There's another trick. So first of all, note that here also, what should I say? There's a note, a second note. Also note that W is symmetric. Also note that W is symmetric. W is symmetric. So therefore, how about this? For the convenience of discussion, we are going to see that because W is symmetric, so we can write now the convolution Now, the convolution can be written as same thing, integral, but I still copy G here, but now, how about here? It's easier for discussion to rechange W. Rechange what's inside to this. No, there's nothing. Theta minus omega. Somehow I find it easier to do this. Okay? Easier for visualization if we change, it doesn't matter. Okay? It doesn't really matter. Can we agree on that? No. We agree on that. So if you do that now, we are finally ready for this visualization. Okay? So we are going to keep G theta right here. But on top of the figure, let's draw a copy of big W. So here we will shift big W to the right by omega. Okay? We're going to shift big W to the right in the theta axis, shifting to the right by omega. Okay? So let's say if this is 0, and we're going to so we are going to shift. Let's say this is our omega. So for one particular omega, we're going to shift big W to the right on the theta axis by small omega. So that is to say we have a copy of main lobe and some side lobe and some side lobe. Some side lobe, some side lobes. So for any given omega, we are going to multiply G and W and calculate the area, right? Because, because this is a bit inconvenient for discussion. So therefore, I just take advantage of this property. Very good question. Okay, this is overall this is generally correct, but here for this special case we can do this. Only for this special case, you are right. Okay? Is that making sense? The way we switch from here to theta minus omega. Okay? There's a reason. This is a reason, a bit easier for discussion. Okay? But just overall, you think about this. Multiplying the two things, and G, what is G? G is so simple. G is simply 1 in the past tense, and 0 elsewhere, right? So G is very simple. So now this evaluation integral goes from 1 over 2 pi. Actually, we only need to consider in between the cutoff frequency, minus omega c to plus omega c. So the integral actually goes from minus omega c to plus omega c, and we calculate the overlapping area. So basically, we are calculating what? We're calculating the area of W when it's shifted to the right by small omega, and now the Tommy variable is d theta. Okay. You see, that's why I need an entire blackboard for teaching. Yeah. So let's just keep moving all my thoughts downward. Okay, but anyway, so for let's say, for any given small omega, for any given small omega, what are we going to do? We're going to calculate the area, not see, we're going to calculate this area minus that area, plus this area, minus that area, so on, and plus, minus this area up to right here. Because when we go further right, it's already in the stop band. So that's the way we visualize it. And now I want to invite you to take a look. Now, imagine that we are going to shift the green stuff to the right or to the left. Imagine that we're shifting the green thing. The green thing is here, right? We're going to shift this to the right or to the left by omega. So please try to imagine what if we shift the first triangle, the main lobe, the outside lobe, shift this, fix the idea from shift the main lobe and side lobe to the right and to the left, or to the right, all the way to the right to go out of the passband. Yeah, or even go all the way to the right to go out of the passband. For this another omega. For this omega, we shift the main lobe and the side lobe, everything all the way to the outside. Okay? Or you can just shift them anywhere in the passband. Or shift it, how about just shift the green thing to the right and to the left. And every time when you shift it by so much, you calculate the overlapping area in the passband. Okay? So the result, this is our color frequency. Color frequency. So the result should be, imagine that if your main lobe is far, far outside the passband, what's the overlapping area? The overlapping area should approach 0. If the main lobe is far away from the color frequency. Okay, so we should expect that when this far away right here, it should be pretty small. And on the contrary, when the main lobe is falling inside the passband, when the main lobe is falling inside the passband, we should expect fluctuation. We expect some fluctuation. 会有震荡. Is that making sense? When the main lobe is anywhere inside the passband, the overlapping area should fluctuate. Why? Because we have side lobes. But in the passband, we expect some fluctuation. But as we move the main lobe toward the edge, it turns out that we will see a maximum somewhere, and then 1/2, and then going negative, and then some fluctuation in the passband until it converges to 0. Okay? The farther we go away, move away, evaluate this integral away from the passband, the more it approaches 0. So we expect fluctuation. So that's my way of visualization. We expect fluctuation in the passband and fluctuation in the stop band until things finally sort of stabilizes. I shouldn't put it towards stabilize. But then the gain approaches 0. Okay? When we move the entire main lobe far away from the color frequency. Yeah? So this is the way I visualize what's going on when we convolve G, when we convolve the ideal response with the first transform of our main lobe, which looks like that. And it contains main lobes, one main lobe with side lobes. Okay? So please, when you go home, try to visualize what's going on. Okay? It helps. It helps. So with that, let's just take a break, and I will ask the TA to give your midterm back. Okay? So your midterm exam has been graded, and the TAs that you do have all the exams about it. Okay. So we take a break. We will take a break.